Well, last time, but during the class, we said we were talking about some logical arguments or that involve logical propositions. But first though, let's go back and talk about a couple questions. Let's try to work on some problems together. So let me just write this at the top. Working together. I just want to see how well you understand this. So try to participate some if you can. So this is from section 1.4. And if you look at page 58 in the book, you'll see question number 34. First of all. So question number 34 says some drivers do not obey the speed limit. So I'm going to leave out the word "the" to save time. So some drivers do not obey the speed limit. So it says to express the negation of these propositions using quantifiers. So how could I do that? Some drivers do not obey the speed limit. So let's just say that the domain is drivers. So when you talk about an X, that means the X is a driver of a car. And let's just say that the proposition P means obey speed limit. So how many does the word some mean?
Not all, but at least one.
Well, that's close. It means it does mean at least one, but it doesn't necessarily mean not all. So like if I said there exists something, that could be one or more. It could even be all. So it doesn't necessarily mean not all, but it does mean that there exists at least one. So that's what I was looking for, is it means at least one. So some drivers do not obey the speed limit. This means there exists a driver X. And what happens to that driver X? Or actually, let me see. We need a proposition that depends on a variable X, like a more fancy proposition, P of X. Right? So there exists a driver X. Oh, and wait a minute. I actually need to make it more fancy than that. P of X doesn't mean obey speed limit, because who is it talking about? There's no variable in that phrase, obey speed limit. So P of X needs to say that X obeys the speed limit. So X obeys the speed limit. So if some drivers do not obey the speed limit, that means there exists a driver X such that what? Such that not P of X, right? So that's what the phrase means using quantifiers. Now, what's the negation of that? What's the negation of in general, what's the negation of the phrase there exists something such that blank? How do you negate that? There exists something such that blank. So if it's not true that there exists something that does something, that means that everything does not do that thing, right? So if there's not anybody who likes pineapple on pizza, that means that everybody does not like pineapple on pizza, right? So the negation of there exists X such that blank means for all X, you do not have blank, right? So the negation of this top one right here is going to be for all X, you do not have P of X, right? So of course the opposite of a negation is a non-negation. So this means for all X, you do have P of X, right? Sorry, I forgot the X. So that means for all X, you have P of X. So now it says to express that negation in English. So what is the negation in English? So the for all x means basically all drivers. And P of x means obey the speed limit, right? So all drivers obey the speed limit. Of course, it's easier to do negations when you don't have words. The English and the writing English is a more powerful language than just so with a lot more nuance and everything like that in it, and like much more complication and stuff. So just reversing these variables themselves is really easy. The English is actually hard. By the way, have you ever do you know what one of the hardest things is for computer science people to do sometimes, or computer cybersecurity people? It's to like, they know all this stuff, but then how do they communicate with other people and tell them what they need to do with their business, or how do they have discussions about planning things and stuff like that? So that's why it's a good idea if you're in computers to also stress learning how to like communicate, and like, why do you have to have a writing class, for example, if you're a computer major? You still need writing classes and speech classes and things like that, because being able to communicate from your domain of cybersecurity or computer programming or whatever it is with the rest of the people that don't know how to do that, that's really important. So language and communication is like the common ground for all of these different fields that you might be experts at. Okay, let me just have you pick a random one. Just pick your favorite letter from B, C, or D. B, C, or D. What's your favorite letter out of B, C, or D?
C.
C, okay, perfect. So let's do 34 part C, and it says this: no one can keep a secret. So first of all, can you just logically, using common sense? I heard some of you talking about how that the homework was just making common sense, and that's mostly true. But once in a while, common sense will actually fail you, because common sense sometimes relies on suppositions that aren't actually completely logical. So no one can keep a secret. A secret. Can anybody think of what the negation of that sentence is, just straight in English without using any quantifiers at all? Okay, that's an example of what makes common sense, but that's not actually the negation of it. No one can keep a secret. The opposite of it is not that everybody can keep a secret.
Some people can keep a secret.
Some people can keep a secret. That's technically true, but how many people exactly is some, though?
At least one.
At least one, right? The opposite of no one can keep a secret is at least one person can keep a secret. Why is that? So no one technically, by the way, no one is kind of actually like saying all don't do something, right? So it's kind of like saying, so let's say if the domain is people, so when you're talking about an X, you're talking about a person, right? That the domain basically refers to what X means. So if the domain is people, and you say nobody can keep a secret, that means your proposition about the X's is X can keep a secret, right? So if it says nobody can keep a secret, that means for all people X, it's not true that they can keep a secret, right? So it's actually a lot like the other one we did. So for all people X, they cannot keep a secret. So that means that's what it means when you said nobody can keep a secret. How do I negate the quantifier for all?
There exists.
There exists one, or at least one. So not just one, I shouldn't have said there exists one. There exists at least one, such that it's not true that the rest of it's true, right? So there exists at least one X such that it's not true that that happens. But what's the negation of a negation? It's just the original statement, right? So this means there there exists an X such that P of X. So there exists at least one person such that the person can keep a secret. That's the negation or the opposite of nobody can keep a secret, is there exists at least one person who can keep a secret. So now you don't really have to say the word there is, you could just say at least one. At least one person can keep a secret. Now, I'm not gonna be ultra technical about the English sentences as much as the notation. At least one person can keep a secret. At least one person can keep a secret. Because English has many ways of saying the same thing. So it's fine with me if you said there is at least one person who can keep a secret. Like I didn't even say the word who right there, but you could say some people can keep secrets. That's also valid as well, because some really just means at least one. But it still has to mean the exact same thing as there exists an X such that P of X. All right, well, the next question I wanted to do together with you a little bit was question 36. So I'm gonna write that one down. So it says to express the negation of these without using the negation symbol. So, okay, so find the negation, but without using any negation symbol. Okay, perfect. So let's just pick your favorite two letters out of A, B, C, or D. Let's pick either A or B and pick either C or D.
B.
B, perfect. And then what about pick either C or D?
D.
D, perfect. All right, so first of all, it says, now I think this book made a comment earlier on in the book that if they don't list a domain, you're just supposed to assume the domain is real numbers. So when they don't say like a specific domain, they're just talking about numbers. So this one says for all X, which means for all numbers, all real numbers X, that it's true that 0 is less than or equal to X is less than 5. Okay, and then part D says there exists a number X such that -5 is less than X is less than -1. So first of all, which of those is true? Is the first one true or the second one true? Second one is true, yep. And the first one, what about the first one? That one's not true, right? Because it's not true that all numbers are between 0 to 5, right? First one saying that all numbers X are between 0 to 5. Second one saying there is at least one number X that's between -5 to -1, right? So obviously if the first one's false, right? And if the second one's true, that means the negation of the first one has to be true. The negation of the other one has to be false, right? So let's go ahead and find the negation of the first one, but without using the negation symbol. So by the way, some students have tried to do this. They just say like, it is not true that, and then they write the original problem down. Is that really the correct answer? No, you can't say like, it is not true that, and then just write the original problem down. That'd be like saying, if you had like a word problem in algebra, would it be valid to write the answer to a word problem in algebra and to say, my answer is the solution to this problem, and then just write the problem down? That wouldn't work, right? I mean, it would be logically true, but it wouldn't be the actual answer because you didn't actually find it. So let's go ahead and negate this. So what's the negation of a for all? What's the negation of the for all? Right, so there exists an X, and what do you do after you change the for all to the exists? You do the negation of the opposite thing. So what's the negation of being between 0 to 5? It would be not being between 0 to 5, right? So what numbers are not between 0 to 5? 0 to, well, actually equal to 0 as well as included. So what numbers are not equal to or greater than 0 or not, and not less than 5 either. So basically, what numbers are not included in that? There's two sections of numbers that are not included in that. Well, let me draw this on a number line because it should be making sense. One of you should have gotten it by now.
0, 1, 2.
No, so those numbers are still between 0 to 5. We're trying to think of the negation of those numbers. What numbers are not those numbers?
6.
Everything else.
Everything else, right? So how do you write down what everything else is? Yeah, infinity. So it'd be negative infinity. Well, except I can't use interval notation, I don't think, in the problem. How about this? What if I just said x is less than 0, but not equal to it, right? Or, remember the symbol for or? X is greater than or equal to 5, right? So the negation of being between 0 to 5, including 0, would be less than 0, but not including 0, or being greater than 5 and including 5 as well. So remember, the negation of something that includes 0 does not include 0. So the negation of something that is equal to 0 does not include equal to 0. But the negation of something that does not include 5, the negation of that does include 5. So every time you have an inequality that has a less than or equal to or greater than or equal to, that changes to one that does not have the equals to in it. And every time you start with an inequality that does not have an equals to in it, it will change to an inequality that does have an equal. And well, it just changes to the opposite. Okay, so the equals to changes to a not equals to, the not equals to changes to an equals to. All right, now is that true or false? Is it true that there exists in X, is there at least one real number such that either it's less than 0 or it's greater than or equal to 5? That's true. Yep. To sure enough, the negation is true. How about part D? What's the negation of the exists operator? For all, right? And now what's the negation of the numbers from -5 to -1, not equal to either -5 and also not equal to -1 either? What's the negation of those? What's the opposite of that?
Less than or equal to -5,
Mm-hmm.
greater than or equal to -1.
Yep. Except not and, it'd be or, right?
Oh,
Do you say and? Yeah. So it'd be either numbers that are less than or equal to 5 or numbers that are greater than or equal to -1. Like that. And is that true or is that false? That's false, right? Okay, perfect. Well, then the next little thing I wanted us to work on together was page 69. Number 9. And this is section 1.5. So this is section 1.5. Okay. It says let L, which stands for love in this problem. Let L of X, Y be the statement X loves Y. Okay. And the domain for X and Y consists of all people in the world. So the domain for both X's and Y's is all people in the world. Okay. By the way, since the world is a planet, have you ever wondered why they don't say it? I'll say all people on the world instead of all people in the world. I'm just having a random thought. So that's all people in the world. Okay, so the first question is, everybody loves Jerry. Everybody loves Jerry. How do I express everybody loves Jerry? With quantifiers. Everybody loves Jerry. How do I say that? Everybody in the world loves Jerry. Well, first of all, I need to, so actually I've already have my, I don't even need to define a proposition because I've already defined my proposition. L of xy means x loves y. That's the proposition. How do I use that proposition together with the quantifier to say that everybody loves Jerry?
For all people X.
Yep. So to say for all x, which means for all people x, because x is defined to have a domain of people. So for all x, what? That person loves Jerry, right? Now, one thing to just be careful about this is just a side note. You can't necessarily assume when you have a proposition that says like x loves y, that doesn't necessarily mean that y loves x. So this is not saying that Jerry loves person X. Okay, that doesn't mean that Jerry loves everybody in the world. That means that everybody loves Jerry. So maybe Jerry hates everybody in the world, but everybody else loves Jerry though. So would this imply that Jerry loved Jerry as well? It would, because Jerry is somebody. And so if everybody loves Jerry, Jerry also loves Jerry. So that's what that means in terms of quantifiers. Now it's going to get harder though. You have to really put on your critical thinking caps on some of them. So everybody loves somebody. Everybody loves somebody. This is going to be a nested quantifier. Everybody loves somebody. How do you say that? So if everybody means for all x, right? So for all x, that means for all people in the world. Now, by the way, once you put a variable after a quantifier, that variable is now bound to that quantifier. So hypothetically, you're not talking about the specific, even though this means for all people, now that person that you're talking about is like a certain person now that you've already mentioned. So once you've mentioned somebody in a quantifier, that variable is bound to that quantifier. You can't use the same variable again to like mean somebody else. Does that make sense? So once I say everybody, how do I say I love somebody? So X represents a certain person who could be everybody, who could be anybody out of everybody. But what happens to that person though? They love somebody, which isn't, you can't use the same variable X to represent somebody, so what variable can you use?
There exists Y.
Yeah, so for everybody, there exists somebody, which you have to call a different name, Y. So for everybody, there exists somebody that they love, right? So that X loves Y. So everybody loves somebody. So for everybody, there's at least one person, so that that person who represents everybody loves somebody, right? By the way, how would I say everybody loves everybody? I can make, what change could I make to mean that everybody loves everybody? If I said for all X, for all Y, then LXY, right? So if I said everybody loves everybody, I would just change the second one also to be a for all. How about there's somebody whom there's somebody whom everybody loves. So there is somebody whom everybody loves. By the way, how do you know the difference between saying who and whom in proper grammar? Put the phrase that it's used in the context of like somebody does something to him. And then if it makes sense, like everybody loves him, it should be a whom. But if it makes sense to say like he did that, then it should be a who. So in this case, it should be a whom. There's somebody whom everybody loves. How do I say that with quantifiers? Well, there is somebody, it means at least one person, right? So there exists somebody. So I've now bound that variable X to that exists quantifier. There is somebody. what's true about that somebody? Such that for all other people, actually including himself, actually. Because the person himself is part of everybody. So there is somebody such that for all people, including himself, that all those people love that person who is somebody. So there exists somebody such that all people love that person. So all people love that person. Right? Any question about that? So it's getting harder. Yes, do you have one?
So what's the difference between A and C?
A and C, everybody loves Jerry. So A is like a specific example of C. So everybody loves Jerry is one specific person that everybody loves. This one is just saying there is somebody, but it's without saying exactly who it is. So it could be Jerry, could be somebody else. It just means there is somebody, but we don't know who it is. So
And I guess, so in C, so it's X loves Y, right?
no, it's Y loves X.
Oh,
Yeah, so everybody is Y, everybody loves X. So the X person might only love themselves, but everybody else, everybody including X, loves X though. Right, because the L, whatever's first in L, well, that's the one who loves. I got you. And the person that the object of their love is the second coordinate. All right, perfect. Now let's try another one. Nobody loves everybody. This one's going to be difficult. Nobody loves everybody. How could you quantify that?
it's not, it exists.
There does not exist one.
At least,
So I don't think you're allowed to use, no, in math you are. You're allowed to say like does not exist with like a line through the exists. But I don't think you're allowed to use that symbol, which is what makes this one hard. So it's so this is like saying nobody does something. How did we do the other problem a few minutes ago that said no one did something? We said everybody did not do it, right? So we could say we'd express nobody loves everybody as everybody. We could express it first as everybody does not love everybody. Right? So if nobody loves everybody, that means everybody does not love everybody. So if nobody does something, that means that everybody does not do that thing. Right? So how do I express everybody does not love everybody? Now, by the way, when it says does not love everybody, that really means there exists at least one person that they don't love. Right? So let me express it like that as well, actually. So everybody has at least one person they don't love. Right? Because if you don't love everybody, that means there's at least one person you don't love. Everybody does not love everybody. Everybody has at least one person they don't love. Notice the more clear I make it, the more words it takes, right? That's the cool thing about English is you can say very complicated things with English with just like 3 words, like nobody loves everybody. But it takes a lot of like to put that into a computer programming language or to put that into a logical sentence takes a lot more words. So everybody has at least one person they don't love. Now, how can I put that sentence into a quantifier? Everybody has at least one person they don't love. We could say everybody is like for all x's, right? That means everybody. Has means there exists. There exists at least one person y that they don't love. Oops, I forgot. There's still a negation in this though. That they don't love y, right? So everybody has at least one person that they don't love. So x does not love that person, right? But there's still a negation inside of that. And what's the whole point of this problem? We're supposed to, well, actually, maybe it said that at the top, but
Last problem.
yeah, that maybe it was at the last problem where we're not allowed to use negations, but it makes it easier if you can use the negation though. If we could not use this negation though, how could we express that though? Well, maybe we couldn't, I don't know. Because there's no proposition that means you don't love somebody. So I guess we just have to say you don't love them this way. So for everybody, there's at least somebody that they don't love. What that, right? Okay, let's see. The ones that get really hard though are ones like G. Look at G. Let's skip ahead to G. There is exactly one person whom everybody loves. How could you say that there's exactly one person that does something?
It exists on with an exclamation point.
Yeah, okay, I told you that actually a long time ago, maybe in the first day, yeah, right. I think I told you too much is more than what you're supposed to actually know at this point in the book, though. How could you say that there's exactly one without using the exclamation point after the word there exists? How can you define uniqueness using quantifiers without just saying that exclamation point that means so the easy way of just saying it is to say there exists a unique X like that, right? Such that for all people love that person, right? That's the easy way of saying it. And that's why that exists a unique thing is so important. If you couldn't say that unique thing, you'd actually have to use some sort of a logical phrase to express this. You'd have to say there exists one person whom everybody loves, like this. So you could say there exists somebody whom everybody loves by saying this. And then you'd say, in parentheses, you'd say, for all, now, by the way, when you get to part of a compound statement, the quantifiers that are bound as part of this. What do you think about that? Well, actually, I guess I don't want to put parentheses around this because I want to actually refer to the same person X actually. So there's this X such that for all Y, all people love person X, right? And for all people, I guess I'll just have to use a third letter actually, because I want to make sure I refer actually to the same people I was talking about before. So how can I say that there can't be another person so that everybody loves somebody else as well? I could say that if there's somebody else that everybody loves, so let me say it like this. If there's somebody else, so for all people named Z, for all people named Z, for all people named, what comes after Z? I'll just say A, such that everybody loves person number Z. If there's anybody else that everybody loves, I could say that that implies that person number Z equals person number X. How's that? Does that work? So there could be for all people that everybody loves in the world, if that happens, if there's anybody else that everybody loves, that person is actually the same person as the original person. So that basically means that there's really only one person that everybody loves. Right? So it's basically like saying if something solves an equation, then it's the same as the original solution. But that's I guess I'm trying to decide whether I want you to actually ever do anything like that, or if I just want you to. I think I'm just gonna say you're allowed to use this from now on, though. Just remember that you appreciate how important and easy that makes it. So there's this unique thing that does something, you can just use the exclamation point after it. Okay, let's see, was there anything else I wanted to have you look at? I did actually. So let's look at page 71. Problem number 26. So this is another good problem for us to think about. So let Q of XY, this is going to be a math statement. Q of XY is a statement x plus y equals x minus y. So when you add them together, you get the same thing as when you subtract them. So that's what Q of XY means. X plus y equals x minus y. Tell me the truth values of these propositions. What's the truth value of Q11? If you add 1 and 1, you get the same thing as if you subtract 1 and 1. You don't, because you get 2, but if you subtract them, you'll get 0. How about what's the truth value of Q of 2 and 0? True, correct, because if you do 2 plus 0, that's the same as 2 minus 0. How about this? Is it true that for all real numbers that 1 plus y is the same as 1 minus y? False, correct? How about, let me make sure everybody else understands that. It's false that always, it's false that it's always true that 1 plus y equals 1 minus y, right? And then how about part D? Does there exist in value such that x plus 2 is equal to x minus 2? Does there exist a value such that x plus 2 equals x minus 2? No, I don't think so, because x plus 2 would actually be 4 more than x minus 2, no matter what, right? I believe that would be false. How about part E? So part E says there exists an x and there exists a y such a q of x and y. So does there exist? So this is actually called the satisfiability property. Is this proposition satisfiable? Does there exist any x such that there can exist any y? That the proposition can be satisfied by anything at all. So is there anything at all that satisfies it? Yes. For example, 0 and 0. So you could say there exists 0 such that there exists 0 such that 0 plus 0 equals 0 minus 0, right? Besides, we already knew that 1, 1 would also satisfy it. So that one's actually true. Okay, hold on just a second. That one is actually true. Let's try G. Is this one true? There exists a number y such that for all x, q of x and y. Is that true? There exists a y value such that for all x's, it's true that q of x and y.
Yeah, 0.
Yeah, right. So this is true because there does exist a number called 0. You were good. Yes, that was a good guess. Such that for all real numbers that if you did x plus 0, you'd also, that would equal x minus 0, right? So this is true with a specific example. True with the example if you picked x equals to, if you picked y equals to 0, that would work actually. So as long as there's at least one time it works, that means it's true. Because the quantifier there exists only needs to be true at least once in order to be completely true. Okay, so for H, for all y, there exists x such that q of x, y. This is basically looks the same as the one before, but is it actually the same or not? If you switch those around, does that always have the same truth value or not? So is it true that for all numbers y, there exists an x value such that q of x and y? No, because if you pick a number like 2, for example. If I pick 2 for the value of y, then that would be saying that x plus 2 would equal x minus 2, which would never be true, right? Because you can't have a number that's 2 more than something be equal to the same thing that's 2 less than itself, because there would be a difference of 4. So that's actually false. So you cannot always have the same truth values necessarily if you reverse the quantifiers. Okay, then I, for all x, for all y, cube xy, is that true? Is it true that x plus y always equals x minus y? No, that's not true, that it always equals, so that's a false statement. Okay, well, now, let's go ahead and talk about this table that's right here on page 76. If you have your book, you can turn to it. This is logical rules of inference. Let me see if I can bring it up for you on the board. Let me just check something real quick. Let me go to this thing. Okay, right here. I'm going to stop showing this whiteboard, and I'm going to. By the way, does anybody remember how to silence notifications on an iPad? I forgot how to do that. I know how to like mute them, but oh, well, I guess I'll just take a risk. Okay, so going to stop this, and then I'm going to share. Oh, I know what to do. I know what to do. Okay, I will just take a picture of it. Actually, I'll make a bigger picture, actually. Okay, now share. Okay. Okay, can you see this now? There we go. Okay, so here's the rules of inference. Let's talk our way through these rules of inference and see if they make sense to us a little bit. So modus ponens, that's basically, you know that there you have an implication. So if you have B, then you have Q. So what a logical argument consists of is it's a sequence of propositions, and all of them are assumed to be true except for the last one. So the ones above the line they're all assumed to be true in a logical argument. Like, this is my evidence of blah 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 blah, and you're trying to use that set of evidence to prove the conclusion that you want, but you don't know if the conclusion is true. So that the bottom line, the thing under the line, that's a conclusion that you want to prove true, but the only thing that you know that you can assume is true or that you know is true are the ones above it. So if I know that P implies Q, and if I know that P is true, that's actually, is that enough to prove that Q is true? Yes, because you know for sure that P implies Q. Like, for example, if somebody drives 1,000 miles in their car, and you know that that's true, and you also know that if you have driven more than 500 miles, you have to refill your gas tank at least far away somewhere, right? You have to buy some gas, or you have to pour some gas into your gas tank at least once, right? So if you know two statements, if you drive more than 500 miles, you have to put some more gas in your tank, and if you also know somebody did drive more than 500 miles, then based on those two things, do you know for sure that they put some gas in their tank, some more gas in their tank? You do, right? So this one makes sense. I think I can actually write on this. Hold on. Yeah. So this one makes sense. This is like saying that if you drive over 500 miles, you need to fill up your tank at least once to put some more gas in your tank. This says like you did drive more than 500 miles above it. So the order doesn't necessarily matter. So as long as they're both true, then you can know that that outcome is true. Okay, then there's modus tollens. How does that work? Some of you actually got confused on this same type of deal a little bit on your homework problems last time. So if you know that, So do you remember the one that said, the problem I asked you, the very first part of the first problem, the one that said, if you get promoted, you'll only get promoted if you wash your cars. If you wash your boss's car, something like that, right? So if you don't have Q, so if you know the P implies Q, what does that mean? If you know the P implies Q, what does that mean? Right? If P, then Q. So does it mean anything if you don't have Q though? So if you don't have, so that's talking about if you have P then Q, but what about Q though? What happens if you don't have Q though? But how do you know the P didn't happen? Can you give me like a logical reason? Because if P did happen, then what? Then you would have Q happen, right? So this is a really complicated argument. So this is saying that if you do have P, you'll always have Q, right? So if P, always Q, right? Always you'll have Q. So, but then do you know that you don't have Q, right? You don't have Q, right? So is it possible to have P though? If you don't have Q, is it even possible to have P? No, because if you did have P, then you would have Q, right? So it's kind of complicated, but even based on Q, you can still know that you didn't have P. So this is actually a valid argument. And sometimes this is called, the next one sometimes called transitive, the transitivity of implications. So if you know P implies Q and you know Q implies R, then actually P also implies R. That's actually the principle of induction, logical induction. So if like one thing, if you have like a card that falls over and knocks over another card, and you know it'll always knock over the other one if it falls, and you know the next one will always knock over the next one if it falls, then you know that the first one will end up knocking over the last one if it falls. So that's called mathematical induction. So we only have one more minute, so make sure you read through those things carefully and make sure that you truly understand why they're all true. Those are the rules of inference. Those are like the rules of like logical argument. So if you're, even if you're a lawyer in a courtroom, your valid arguments need to be based on those structures like that. It's kind of hard to understand though if you're having a logical argument, how to break it down from English though into those basic forms. But those are the basic forms of many, many different logical arguments. So that's where we'll stop today. Have a wonderful day, everybody. And by the way, let me make sure that I go through attendance right after I stop this. I'm going to